Viewers, today we are gonna go to a discussion of linearization, and we want first understand what is linearization. So a linear system is a system that where the input and output they find themselves in a straight line. So we will consider a VI characteristics or characteristic of a diode, and here we'll have a part. We come and have a part which we call an operating point. Like here, that's the operating point. That is a small point where we will consider that we'll be operating with. Also, we have another equation here in our right side, a graph shown there. It have a curve on that graph. So we will take an operating point from 5 in x direction, 5 to 10, and then in y direction from 7 to 12. So after taking that, we will come here and understand what's the assumption that we make, and we'll have, and then the variable derivative on a very straight tree for some operating condition. So we will consider if we have chosen, like in our right part here, in this graph here, we'll have an operating point. Operating point where we'll consider y is varying from 7 to 12. So we need to work with the mean point, which is x bar, or y bar, which is a mean value of that range. So also we will come and employ the Taylor series expansion, where we have y is equals to fx bar plus fx over x, and then change of x. So in this way, as we have learned in mathematics, we'll discard all the higher orders factors. So that's why we have this y here. Let me show you, maybe before y is equals to fx bar plus df dx x minus x bar, and then plus the other higher order derivatives. And then we come in here and say all derivatives are evaluated at a mean operating point at x is equals to x bar, which we said is a mean value. Is a very small for higher orders. So we'll come those many stories, and nonlinear system, that's what we want. It have two inputs, which is x and x1 and x2, and then we will come and see the higher orders. We are discarding them and just employing the first order here, where we have x minus x bar. So we'll come, let's try understand this using an example. There is this equation here. This is the main equation that we'll be using in everything that we are doing here. So knowing about that equation, we just come and say, like, we come and say in example 1 says linearize z is equals to xy in the region 5 ranging from x ranging from 5 to 7 and y ranging from 10 to 12. So we'll come and have the mean value, which is x bar, which is 5 plus 7 over 2, which is equals to 6, and then y bar is equals to 10 plus 12 over 2, which is equals to 11. So to get z bar, you will just employ these 6 and 11 in every place. We said here up, we said there is somewhere here we have said, let me see and then explain to you. So here we said, like, we are using all derivative are evaluated at the mean operating point, i.e. at x is equals to x bar. So that's what we are doing here. That's what we are doing here. This is just our original question here. How to get the z bar? We just employ the mean values, which is x bar and y bar. So, and then we come and put 6 multiplied by 11, which is 66. And then we come to the step 2. Step 2, we come and get the df dx when x is equals to x bar and y is equals to y bar. So we come and differentiate that equation z with respect to x. And then we have, when you differentiate it, you just have y, because that is x is raised to power 1. So, and then you put that y bar, which is 11. So k1 will be 11, and then k2 df dy, you differentiate with respect to y, so we will have x, and we have said we are working in x is equal to x bar and y is equals to y bar, which is 6. So k2 is equals to 6. So step 3, you get z, which we said this is our main equation here, this one here. So we employ, we say z minus z bar is equals to k1 x minus x bar plus k2 y minus y bar. So z bar, we got it from here, here, right there, and we have employed it y minus 66, what we got there, and then we have k1 is equals to 11, we have x minus x bar, which is x bar is 6, and then we have addition of k2, which is 6, y minus y bar, which is 11, and then we'll come and find this one here, that is our z in a linearized mode. So we can need to verify, so this is not much common in our exams, but we can have it. Maybe wait, let me just explain. When x is equals to 5 and y is equals to 10, so you put 5 and 10 there, and then in the linearized fashion, linearized equation, you put x is equals to 5 and y is equals to 10 as you have given to verify that. You will find like we have 50 in the exact value and we have 49 in the linearized approximation. So the difference is 1. So that is the error is 1 divided by 50, which is 0.02, which is 2%. Thank you. In the next video, I will be doing the second example. Thank you. Keep tuned to my channel. Subscribe if you have not subscribed, and like, comment, and if you didn't understand something here, just consider asking me.